Okay, so once again, let's just go through these group numbers here, and then we have one more slide. This is it. For bromine, we are in group 17. This is a halogen. Rubidium is in group 1. Aluminum, group 13. Sulfur, group 16. Germanium, group 14. And helium is in group 18, but keep in mind, it only has an atomic number of 2, so it has 2 electrons only. It cannot have an octet. So remember, with any of these teens here, all you do is you subtract 10 from all of these to get the number of valence electrons. So you're going to have 7 valence electrons in bromine. You'll have 3 valence electrons with aluminum, 6 for sulfur, 4 for germanium, and then we only have 2 for helium. Okay, so what do? We put these together just like we would if we were filling P and S sublevels using the arrow diagrams. And this helps us to know, or to be able to see if you know where those electrons are really going within the orbitals. After we learn this placement of electrons, when we get to the bonding chapters, we then can feel free to move these dots around some. So with bromine, I've got 7 valence electrons. Remember, there's a max of 2 on each side. These are my S electrons, px, py, pz, px, and py. Okay, a max of 2 on each side. You can't have any more than a total of 8 for an octet. So bromine is shy 1 electron of an octet. And keep in mind then, that's going to be a highly reactive element because it's going to really draw those electrons toward itself in order to complete an octet. All right, so rubidium, group 1, well, that means it just has 1 s electron. It doesn't really want to keep that electron a whole lot, and that's why rubidium is very reactive. Plus, rubidium is toward the bottom of the group, so it's going to have a larger atomic radius. Keep that in mind. Aluminum, you have your 2 s electrons and you have your 1 p electron. That's a px electron. Okay, so it's a metal with 3 valence electrons. Sulfur, group 16, 2 s's, px, py, pz, and px. All right, so the way we're filling these, px, py, pz, px, is following Hund's rules. So we're trying to really reinforce those rules that you learned in the 4th chapter. Germanium, 2 s electrons, a px and a py, just like carbon. And then helium, of course, just has 2 electrons, so you cannot put an octet around it. And some of you were caught on that on your test for the chapter. Okay, so in Thursday's class, we were going to add an extra problem to the back of that sheet. I forgot to put in a specific heat problem when I wrote this review. So if you would, please put this on the back of your page. You can pause right now to add this question. I don't know if I have enough room to work this on this side, but it's a very clever problem in terms of pulling in a lot of things that you've learned so far this half a year in chemistry. So we're looking at the specific heat of a substance. And what you have to remember for specific heat is every single material is going to have a unique specific heat. And the definition of specific heat is the energy that's required to raise 1 gram of a substance 1 degree Celsius or 1 degree Kelvin. Okay, so it's very unique. And of course, the only specific heat you have to know is that of water, which is 4.184 joules per gram times degree Celsius. Okay, and it just so happens in this problem we are dealing with water. Now, don't be thrown by this Kelvin, because truly it doesn't matter if we look at Celsius or Kelvin. We just want to make sure that we're keeping it all straight. Okay, so if you're looking at this, you have to really be sure to tie these things together. When you see joules, kilojoules, what you always have to remember is that is going to be your energy. Now, when we talk about energy with specific heat problems, our energy is going to be referred to as Q. All right, so our Q is going to be equal to 980 kilojoules. Okay, now if you remember specific heat problems, kilojoules is not the unit that we want. Joules is the unit that we want. Okay, so really what that would translate to is 9.8 times 10, and think about this, there's going to be 1,000 joules and a kilojoule, so you're multiplying by 1,000, so that would give you 980,000. This zero is not significant, so what you'd end up getting then is 9.8 times 10 to the 5th joules. Okay, you could also use a conversion factor to get that. Now, it's kind of interesting because we have a volume here, and that might leave you a little bit perplexed, but let's just go ahead and write that down. So we've got 6.2 liters of water. Okay, now if you look at this, you read the full problem, this is going to be your key. There's a hint here that tells you, well, the density of water is 1. So if the density of water is 1 gram for every cubic centimeter, what that means then is that every gram of water has a volume of a centimeter, every cubic centimeter of water has the mass of a gram. So if you've got 6.2 liters of water, that's 6,200 milliliters, that's 6,200 grams of water. Okay, so I go from 6.2 liters to 6,200 milliliters of water, and then from there I just simply go right over to 6,200 grams of water. Now this isn't my volume anymore, this is going to be my mass. Okay, now if you know the density of a substance, you can go ahead and do that. Now my temperature is 291 Kelvin. All right, so let's just go ahead so that you can have some practice. Let's just convert that to Celsius. In order to convert that to Celsius, what we'd do is we'd subtract 273. So if we subtracted 273, that would be 18 degrees Celsius. So 18, 273 is going to give us 291. Okay, now keep in mind here, we have mass right here. So this is really RM. Okay, so now in looking at what we have here, what you're going to see is we have a Q, an M, a T. We do not have a C. Well, I just told you the C, and that's 4.184 joules per gram times degrees Celsius. Okay, so let's go ahead and solve this. I've got Q equals mc delta T. That's my basic equation. If I rearrange that equation to solve for my final temperature, what I really have to do is to solve for my delta T, and then I have to adjust my temperature in order to see how much heat is lost or gained. Okay, so I'm really solving for delta T here. So delta T is going to be equal to Q over MC. The queen stands alone on the top. She's the boss lady. Okay, now I'm going to section this off in the hope that I don't have to go to a new slide. This doesn't get too complicated. Okay, so I'm going to go up here. My delta T is going to be equal to 9.8 times 10 to the 5th joules. My C, or my M rather, is 6,200 grams, and that's 2 sig figs if you look up top. And then my C is going to be 4.184 joules. And then since I have grams per degree Celsius under here, I can just flip that up here. Grams times degrees Celsius. Okay, now I'm going to look at my unit cancellation here. Joules, gone. Grams, gone. And I'm left with my degrees Celsius. Okay, so I'm going to punch some numbers here. And remember your order of operations. If something's a numerator, you multiply. And if it's on the denominator side of the fraction, then you've got to divide by that. So I've got 9.8 divided by 6,200. Also divided by 4.184, and that's going to give me a very small number. All right, so I'm going to punch that out again just to double check. 9.8 divided by 6,200 divided by 4.184, and I still get a really small number. So what I actually have on my calculator is a crazy number. I hope I'm right. 0.00, oh my gosh, that's a lot of zeros. One more 0, 37 7. Now I have 2 sig figs here, so since I have 7, 7, 7, 7, I'm going to round this to an 8. Okay, my calculator says 0.00037777, so I'm going to change this to an 8. I have 2 sig figs here, and I have 2 for my energy. Now, my exponent is going to be times 10 to the 5th. So if you look up here, I can't forget about that exponent. Okay, now this is going to be a temperature. So what we've got to do here is we've got to arrange this 1, 2, 3, 4, 5. Okay, if we take this and we move our decimal 5 places over, what we actually have is 38 degrees Celsius. And you have to keep in mind that this is my delta T. It's my delta T. So this is how much the temperature has changed. This is a positive number. Okay, so that means what happened is my temperature went up because I'm adding energy. Okay, so I just go back to my initial temperature, and that initial temperature is right here. I could mark this initial temperature to clarify things. And so all I do then is figure out, okay, if delta T is equal to TF minus TI, how do I solve for TF? Well, of course, TF is going to be equal to, and you can do this a variety of ways, but I'm just going to say TI plus delta T. So you're going to have 18 degrees Celsius plus 38 degrees Celsius equals 38 plus 18, 56, I hope, yes, 56 degrees Celsius is going to be your final temperature. Now, if you wanted to convert that to Kelvin, you would actually just add 273 on, and you would get 329 Kelvin. Either way you answer this is fine, but just make sure if you're going to use a K here, joules per gram times degrees Celsius for your specific heat, that you stick with a K all the way through, or if you stick with, you have a C, that you stick with a C. Okay, now the other specific heat problems that we did in terms of the calorimetry, conceptually you need to be aware of those, but you don't have to be able to solve one of those for your semester exam. Okay, so that's all I have to say about that, and I hope you viewed these because I really want you guys to do well on your exams, and adios and happy second snow day.